Well, good morning, everybody. Thanks for coming along. It's good to see a full house. After the week's hardcore sessions, I think this one's going to be quite a bit of light relief. There's going to be no template metaprogramming. I'm not going to be talking about edge cases in the syntax of the language or anything like that. I'm going to show you some C++ magic tricks and then give away the secret. So, it's a 45-minute session, so most of it I'm going to spend doing a demo, and I'm going to try and go quite quickly at the start, so we've got time for questions, because last time I gave a talk about this, we had a lot of questions. I'm going to show you some crazy C++ voodoo, but before that I'm going to spend about 10 minutes just talking about the background, the work that led up to this, the platform I've come from, and the problem I was trying to solve with it. Then I'm going to explain, then we'll do the live demo, and then I'll go into the dirty details of actually making it work. So, my background for the last 10 years has been based around this big C++ library called JUCE. It's the best way to describe it is a bit like Qt. It's one of these big top to bottom level, every level from the GUI down to the collections and the low level stuff libraries. We got GUIs, graphics, lots of audio in there because the the library spun out from an audio workstation project that I built back in the early 2000s. And it covers pretty much, it's one of these one-stop shop kind of libraries where pretty much everything you need for an app is in there. And it's mostly used in the audio industry. So outside of that, it's not very well known, but in the audio industry, pretty much all audio plugins and audio apps will be built with JUCE, and video too. So probably if you listen to a record that was recorded in the last few years, or go see a modern blockbuster movie, there's a very high likelihood that somewhere in the production of that, some JUCE-based software will have been used. This talk's not really about JUCE. I could talk for hours about it, but there's plenty of information on the website if you want to dig into that more deeply. I will talk briefly about the architecture of the library. It's according to GitHub, it's about 650,000 lines of code, so it's pretty big. And a few years ago, I divided this up from one big lump into modules. So we've got about 15 modules now for the different areas. In order to, what I would like to have done with the architecture is to make the whole thing header only, like Boost and a lot of the STL. But with it being cross-platform and having to support some crazy kind of internal tricks to get things working on all platforms, that's not always possible. So the way it's architected is the kind of second best, which is to have each module works as a header file and one or maybe no CPP files. And these things get directly included into the target application. Each module is also has a manifest to describe its format, and that allows for tooling, which I'll show you in a second, to automatically include these set headers and CPPs into target projects. The library used to be static, a static lib format, but I switched to this module architecture with the direct inclusion because most of the use cases for my users are they're generally building a product that runs on at least 2 or 3 platform operating systems, each of which is using a different compiler or IDE, and they're probably building several versions of the same thing, all of which need specific settings, and so building and maintaining all these libs on all these different compilers is a bit of a pain in the neck. So the module format also means we've got some third-party libraries being written by other people as well, and I'll show you in a second the tools that we have for managing those. Apologies for the terrible puns, but just to explain a few things. The introducer and the Projucer. The thing I'm showing you today is the Projucer. This isn't released yet. The introducer I'll show you in a second as the basis for this, is the IDE type application for JUCE. And that's been around for a few years. This thing is there because it solves the problem of managing your cross-platform compiler projects. When if you're running on 4 platforms and you want to add a CPP file to your project, it's a central place where you go and add that, and it regenerates all of the the compiler-specific projects for all the different OSs. So you have one central place where you set up your project, and then it'll spit out Visual Studio, Xcode, various other projects for the targets. It also manages these modules and has lots of helpful things for beginners, like things that will set up a JUCE application or a plugin. I'll give you a quick run through the introducer. Can you see that? So it looks like an IDE and acts like an IDE, but doesn't do any compiling at this stage. Like an IDE, you've got your files on one side, source editor on the right, and a configuration page where I set up things like Xcode, Visual Studio settings, and also this page for modules, which is where these are the JUCE modules, and you can tick which ones you want to use, and it'll automatically generate the right headers and include those headers in your project. For the ones you tick, it'll manage the dependencies, that kind of thing. Now, also in here is the JUCE's old GUI editor. Now this has been around for many years, and like any GUI editor you've ever seen, this one has a simple layout, a little repertoire of things like buttons, sliders that it understands, and everything's like statically laid out. And it's not very flexible because, as you can see, like as soon as you have a custom component, it can't show you the component. It can just show a placeholder. The way this works is from the document that describes the layout, it generates your CPP file, and off you go, and then you actually fill in all the custom stuff. But the editor itself is pretty inflexible because I find that, I wrote this years ago. I hardly ever use it myself because all of the things I end up writing tend to be custom dynamic components. So you have child components that move around, you have complicated layout algorithms, and this thing can't represent that. So people use this, but it's good for dialog boxes, it's good for simple stuff. But I've been trying to come up with a better way of doing a GUI editor than this. So I spent a couple of years trying to come up with an extension to this that would let me do more complicated layouts. And I was experimenting with things like having an expression language for the positions of these objects, and maybe even like the road that Qt went down was to have their own QML scripting language to do layouts. But I found that as soon as you started making these languages complicated enough to do the stuff I needed to do, you were back in the same problem of the GUI editor couldn't handle it because it's just an expression or just a piece of code. So it didn't really help. It made it easier maybe to write the script, but then you still end up with just your C++ and then a layer of scripting on top. So I was trying to come up with a better solution for this. And then last summer, there were a couple of videos that came out and did the rounds on the developer forums. There's a guy called Brett Victor who did a demo called Inventing on Principle, and this is massively hyped. It was all over the forums, and basically what he had in this demo was he built himself a little mini IDE based around JavaScript. So on one side of the screen he had his JavaScript editor, and on the other side he had the output of the program that he had there. His first example was to draw a picture of a tree. So he had code to draw a tree, picture of a tree. Some of you probably saw this. And then he pimped up his editor so that you could pop up a color selector on some of the literals that were a color, and a slider on things that were a floating point number. So as he whizzed these sliders around, every time the code changed, the picture was instantly updated. So you could move these sliders and the tree would move around. And he had a few other tricks, like being able to click on the picture and then go back to the line of code that drew that part of the picture. And so I was watching this and thinking, this would be so useful for the kind of things that I do most days, the kind of custom GUIs that I'm doing. And then shortly after that, there was another bunch of guys called Lighttable, who you've also probably seen, got very big, lot of hype. And they were doing the same kind of thing with closure. It's very easy to do this sort of stuff in JavaScript. So I was looking at it going, you know, I could really use this, but it didn't seem like there was really any chance of being able to do this in C++. And it's unusual for us C++ guys to actually ever hit a roadblock and see something you can't do. So I felt a bit irritated about that and dug around to see what if there really was a way. So I got hold of the LLVM JIT stuff and Clang, and just played around to see what I could do with it. So, without any more whiffling, I shall fire up the Projucer and show you what I ended up with. So I've prepared a few simple demos. For the first one, I thought, because this was inspired by the Brett Victor tree demo, I took his code and I'm going to do it in C++. This is it. It's not very much. Little class that draws a tree. And the class itself is a JUCE component. Component is like the it's sort of equivalent to a Q widget or a, you know, an NS view, that kind of thing. The JUCE components, they actually look a lot like Java, which was fashionable when I was designing this. So in the Projucer, it's constantly recompiling your project, and as it compiles it, it scans the abstract syntax tree for interesting classes. So down the side here is a list of the component classes that it's found in compiling this little app. At the top here, it's found some of the demo things I've written, and the tree picture class is there. Some of these are grayed out because some of the classes can't be instantiated on their own. They might not have a default constructor, they might be abstract, might be templated, or some other basic reason why you couldn't just create one of those classes. But the tree picture one here is instantiable, so I can double click that and lay this out so you can see what's going on. A bit squashed with space on here, but let me put that right there. Well, I made it big so we could read it, but okay. So it's not too important, but okay, I'll make the window smaller. You can see the tree anyway. So like Brett, I've added stuff to my editor so that you can do things like adjust a value with a slider. So as I move these around, I think there's a colour up here somewhere as well. So I think this is the back. I think this is the sky colour. Sorry, what? Like that? Oh, sorry, because you're behind people's heads. Okay. So
this is being dynamically recompiled?
Well, I'll explain in a moment. There's two things that can happen when you edit the code. First of all, what I was doing there was just changing a literal. Now, when it scans the syntax tree during the compilation stage, what it's done is it's also created a little database of all classes and the code locations of things like literals. So when I was editing those bits of code, it could see that the only change to that file was a literal. It could then go to the database, find out where in the JITed code that literal was going to be running, and just poke the memory directly. So it's really just setting one integer or one float in the running JIT code without interrupting us at all. Of course, if I make a syntactical change, so let me, this is, no, not there, I'll put something in the paint routine, I'll make it draw something else, say, draw a rectangle like that, then it had to recompile it. What it did was it recompiled just this source file. It's also automatically found as many precompiled headers as it could pull out of there. So it recompiled that, closed down the old JIT engine, links everything against all the rest of the code base for this project, which was already cached on disk as bitcode, links it all together, reloaded it into the JIT engine, instantiated that class again, reloaded this window, and that takes about, I'll change the color so you can see the time it'll take. So if I make that green, and I'm going to recompile now, about 1-2 seconds, and we're back running. So this kind of gives you the ability to tweak around your graphic layouts with a window over here showing the output, and you're tweaking things around. Occasionally you just look over and see if it's right yet. So some things will happen instantly, some things won't.
Why do you have to recompile and change the color? Wouldn't that be, I guess it's not literal.
The question is, why does it have to recompile when I change the color? Well, that's actually a symbol. So if it was a literal, I could have. So changing the other color here, this is a literal. This was actually a symbol. So there was no way the editor at the editor level that you could say, oh, this is only a literal. I don't have to restart. So I mean, even if I add another semicolon at the end there, I mean, there's no actual change, but it still has to do the recompile. Yeah.
So, have you tried to characterize the class of applications that can benefit from this kind of interactivity? I was thinking, I've been working on this horrible subversion of JIT conversion process. Right? It's a big process that has to turn through a whole bunch of stuff, and right now I can't see any way that I can apply this to that. So there's got to be some characteristics of the application that makes this really work.
The question is, what's the characteristic of the application that makes this suitable? Well, initially my motivation was graphics and component design, because that's what I do a lot of, and that's a place where it's obviously useful. But so having written it, I'll talk at the end about some of the other things that could be done with this. The thing to note is that everything in this window is running in the JIT compiler. The editor on the left, all of the stuff that adds the rulers, the buttons, and the extra things that does more, which I'll show you in a moment. This is all running in the JIT. So this code is all dynamically compiled. And this doesn't have to be a GUI editor. It could be anything. You can write your own editor for whatever you want. So certainly things that I'll be adding to this later will be an audio editor. If you're writing a synthesizer, you might want this window to show a little piano keyboard, a little window at the top showing the output, some graph of the audio coming out, and then you can tweak your audio algorithm over in one window and listen to the result in the other. And it could be, if you're writing a web server, you could have this showing the output of whatever your web code is doing.
So the audio example is a lot like what I'm doing, in the sense that you'd have to say, okay, I made some changes, start the process again. And
Yeah.
you sort of start over from the beginning. You don't get this kind of seamless experience of there's the code, there's the update.
Yeah, the comment is that there are other situations where it's useful to not have to restart the whole cycle of recompile and go through it again. And yeah, there are probably many uses for this that I've never come across. So yeah. Yep. Yep. Absolutely. Yeah. The comment is that unit testing would be great for this. It would be perfect. You just have a window on one side telling you whether your code's right at the moment. Occasionally, you just look across and it's either red or green, and it's saying OK or fail. And you don't actually have to hit a button to make that happen. It's just being recompiled. Yeah.
Just for the record, with the unit test, imagine having to split your code in the test code. So UI is the organization of So your code is colorized based on coverage, and the text is colorized based on accuracy.
That's yeah, the comment is you could split the pane and colorize your code and test code based on different criteria. That's the thing. Because this is a window where you could put any dynamic bit of code in, we could sit here all day and come up with uses for it.
Are you able to those two
I'm going to tell you some. I'm going to show you some of the other tricks it can do first. But you've got a question? Okay. Okay, give me a minute. Maybe we'll get to it. So that's a simple example of just something that draws a picture, and that's live coding. But we can go beyond that. We can do coding that's not just live but self-aware. So this next example this looks a lot more simple. This is just a dialog box, but it's got some subcomponents. So let me pop up the code for that. So a very simple little class, just has a few child components, OK button, that kind of thing. Now, when it's doing the compilation and building the class database, it also squirts in some extra code to let these running components find out about their own structure. So it's not full reflection in there. It just gives it a few things that it might need to know. So for this button here, there's going to be code that can be called that lets this button find out where its bounds were set and where it was created and where the member variable that represents it lies in the source code. It also has an API that it can call, which will let it change the original source code that created it. So what I can do is grab this button, and once it's a little recompile, I can drag it around, which, not very surprising, GUI editors do that. But what that's actually doing over here is this line here is where that OK button has its bounds set. And if I can get this all on the screen at the same time, if I move the OK button around, it's actually the only thing that happens when I move it is it goes back to the code and edits the code. In this case, those are all literals that's changing. So those literals can get injected straight through to the running JIT code, and the button moves. And it really is, there's no trickery. It really is, the feedback is a full circle via the editor and back through to the JIT engine. Another thing you need to do in the GUI editor is add a new class, add a new child component. So we can do that here as well. Unlike, in a normal GUI editor, you have a repertoire of buttons and well-known classes that it can handle. Here, it doesn't need to be limited to that because it knows all the classes in your application. So these are all the things you could possibly add. At the top, I've got some of these classes at the top. These are ones that are little demo classes. So I can actually add my tree picture to the parent component. Because it's actually going to edit the code, it shows you a diff just to let you sanity check what it's going to do. So it's telling me here that if I add this tree picture, it's going to call it tree picture, it's going to add a member variable to represent it there, it's going to add it to the parent, and it's going to set its bounds. So if I say OK, it's gone and it's edited the code, and that's been recompiled already, and there's the tree picture. And of course I can change its bounds, move it around. Adding, oh sorry, go on.
Is there some analog kind of feedback mechanism you can have when the layout is a computed layout?
The question is there some sort of feedback when the layout's a computed layout? Thanks for mentioning that. Thing I should have mentioned before was these buttons here. If I change the parent size, they're stuck to the bottom. And the way that works is that they're very simple. In their set bounds call, their Y position is based on the height of the parent. So when I'm moving it around, it's not just what it's doing is it's looking at this whole expression and saying, okay, for the y position, there's something minus 84. It can't really know, that could be anything. That could be a variable, it could be a big complicated expression. But it can, if it recognizes a pattern such as a simple expression with a constant, and if it can change the constant to get the value it's aiming for, then it'll change it. If it can't do that, I mean, if these were really ridiculously complicated expressions, it would just give up and not let you move it. But in the cases that I've come across where they are really complicated bounds, you don't want to pull it around with a GUI editor anyway, because it's probably animated or doing something really customized. I'll fire up another version of that same, a similar version, just to show the fact that this is the same panel as before, but with a little bit of animation in it. So I've just put box 2D in there to do some animation. And the point here is that you can see here's a list of child components, and these are changing. The thing that you see in the GUI editor is not a laid out version of a representation of your component. It's the real component actually running. So these things could be running threads. They could be running OpenGL. They could do anything they want within their space. And the editor is wrapped around it, running in the same process as the component itself. So the question is the requirement to add a default constructor? Yes, it is. The way it works is the classes are getting pulled out and instantiated in isolation from the normal running of your program. So, yeah, it needs a default constructor. It needs to not crash when you create that class on its own. It needs to not rely on things being around that it expects to be around. It can't be abstract. There's a lot of limitations. If you want, it does also support a well-known static method. So if your class has a static method, I've forgotten the name, but create Projucer instance or something, then it'll look for that. If it hasn't got a default constructor, it'll look for that, call that, and that should return an instance of the class. So if you want to create a little sort of test wrapper around your more complicated component, then you can add this static function, if def it out for your release version, and have it. It could even create a little set of statics that it needs and hack things together so that your component will happily run. But just showing over here, it's got a little ball generator that works from the position of the OK button, and as I'm dragging it around in the editor, it is actually following it. And also, if I'm quick enough, I can probably rubber band select some of these balls. So if I was quick enough to grab them, it would try to move their bounds. So the whole thing is really dynamic. The question is which bounds of the ball. It would depend on. I can't remember how I've set the bounds of those. There'll be an expression in there somewhere doing it. It'll probably be an expression that it can't actually move, to be honest. You're inevitably going to write code that crashes. So this window with the editor in is all running in the child process. If you do something stupid and then it crashes, the IDE can just realize that the child's gone away and reinstantiate it and just carry on. So it takes a few seconds to do that and doesn't really interrupt your work, so that's pretty good. The question is, what do I use for this process communication? I'm actually using some JUCE library classes for that. There's not a lot. On OS 10 it'll use a socket, I think. Yeah, I think so. Yeah, on Windows there's probably a named pipe. I'm not using any boost in here at all, I'm ashamed to say. This is all completely. This is just JUCE and LLVM.
So you wrote your own message passing.
The question is, did I write my own message passing? Yeah. Well, I didn't write it for this. I already had that. Yeah, it's all in-house. One other thing I want to show while it's open is what I was saying about the modules and the efficiency of packing an entire heap of code into taking like the whole library's 600,000 lines of code, packing it into 15 modules. I'm just going to recompile this entire project. I'm going to start now. And that's compiling the whole library, and the little couple of, it's finished. And the bits of demo code there, compiling it all, linking it, and it's just, it never ceases to impress me. The fact that if you take the whole library as individual compile units, sorry, the question is, what made that so fast? If you took the whole library as individual compile units and did each one, it's going to have an overhead for each one. But by packing it down to about 50 to 100,000 lines of code per CPP file, as these modules work, it kind of hits a sweet spot for the compiler. I've tried actually doing the whole thing in one CPP file, and that's okay, but it uses a lot of memory. But if you have about 10, 15 is the sweet spot. And on here, I've got 8 cores on here, so it just does them all in parallel. And each one compiles in maybe a second. So it just all works very nicely like that. The question is, are there precompiled headers? When I did that, no. But when you're editing a source file and it's rebuilding the JIT from it, yes. It does all sorts of tricks where it knows, the editor knows which file you're messing around with. And for that one, it makes sure that all of the other modules and compile units in the project are all safely compiled down to bitcode, stashed away on disk. The one you're working on, it looks at the headers and sees how far down it can get before it hits something that isn't a header or a header that you are also working on. And so all the system headers, it'll tend to be able to precompile. So it does that, stashes that all away. And it does that opportunistically. So wherever it can find something it can precompile, it will. But when I did the full recompile there, it just blew all the intermediates away and started again.
I guess I have another question on the JIT part of it. I'm not quite sure I even know how to ask the question properly, but I think about a CPP file as a compilation unit, and yet if you change a method where the only thing you were affecting did not exceed the bounds of that method, local variables, etc., is the JIT intelligent enough to just recompile that portion of that compilation unit?
Okay, the question is, if I was just to change something within the boundary of a function so that it doesn't affect anything outside that function, is the JIT smart enough to deal with that? At the moment, it doesn't. At the moment, all I can do is recompile the whole file. What I would like to do that, and hopefully one of the things that the LLVM project will do in the near future will be to make the LLVM context objects multi-threaded. Because what I need to do for this is I have multiple threads going, and at the moment with LLVM, once you've built something in one context on one thread, it's difficult to pass bits of that compiled syntax tree around to another one. So when I've got my execution engine running, doing the JIT on one thread, I need to be recompiling the source code on another one. And it'd be great if I could just say, okay, compare these two abstract syntax trees. If the only change is within the function, I'll reload the function. The JIT engine does provide a way of reloading a function, but the difficult bit for me is to find out which function it is and to get the new function across between threads. So that's something that hopefully I will be able to do, but it's already pretty quick. I mean, to reload the JIT engine in about a second, even if I added that, it wouldn't be much better. It'd be a nice thing to do, and for myself, I'd like to do that. But it's it probably wouldn't make much difference in most cases.
I just want to make sure that I totally
Yeah. Do you want to do it again? The question is, was that really a complete build of 650,000 lines? Yes. Here it goes again. Those are the modules going by. And now it's just doing the linking. That the main.cpp was this demo app, and it's done. And while it's doing that, it generates class database for each of the compile units, which is what it pulls this thing here out of. What else can I show you? There's I might actually show you the. I'll show you the Projucer running the introducer, because the great thing about this is I've thrown all sorts of code at. Oh, sorry, question. I've got. Sorry, the question is, given time constraints, have I covered all the really dirty stuff yet? I've got a few comments later, but freeform. If you got anything in particular you want to ask, fire away. What I was saying was, I've thrown all sorts of nasty code at this, and it seems to cope with it really well. The introducer was never designed to run in here, but you load it in and it pulls out all these classes, and some of these will actually just are instantiable. Let me see what I've got in here. Which one? I don't know. I can't actually remember what that is. So it's just a box for editing UTF-8. So it's just used in this is just a little part of the introducer, which is a tool for converting a string into a UTF-8 string. But that seems quite happy to run on its own. And it's amazing how many classes you do actually work. Let me go back to my slides. So, sort of observations on this. It's interesting in using it myself. I find that it kind of forces you into good habits. Because if I'm writing a component and I know that I want to play around with it visually, I'm going to have to give it a default construction. I'm going to have to avoid state. I'm going to have to make it not depend on other bits of the program that aren't going to be there. And it really forces you to decouple and think about things differently. So it's actually quite good discipline to use this. I've also found myself writing simple GUI wrappers for non-GUI code. So occasionally I'll be working on something that's I'm trying to get an algorithm right. And rather than just going through the whole compile test process again and again, I think, well, it'll take me 5 minutes to just knock up a little component with a paint routine that just prints out the result of this algorithm, stick it in a little test project, pop it on one side of the screen, bash away at the algorithm until it's right. And once you've got the facility for doing that, you start noticing you come up with ways to use it. Observations on the nasty bits. I don't think you could do this unless you're in the kind of position I'm in, where I've got control the whole chain down from the editor, the library, and the JIT engine. To actually do the round trip, you have to know. The editor is sending diffs in terms of, it knows exactly which bit of code has been changed, and it has to keep in sync with the class database that says, here are the bounds calls, and here are the source code positions of those. As the code changes, all of those positions have to be kept updated between the GUI editor moving them and the editor moving them, and you really need the whole chain from top to bottom. And also, you need some sort of library that knows what's going on and has been modified to actually do the graphics. So, unless you actually were in charge of that as well, it would be quite hard to do this with a third-party library. It would be quite easy to add other libraries into this. So if you were trying to write something that was not JUCE-based, but which you wanted to debug in this way, you could quite easily add add your external code to a simple JUCE-based wrapper process. We already talked about PCHs. Already talked about threading in LLVM context. Lazy JIT compiling is something that the LLVM people seem to want to get rid of. And this whole thing depends on that. The way they'd like it to work is that you load the JIT engine and it goes through and compiles everything or to machine code, and then you can call a function. Sorry, question.
So that's a side effect of moving to the new MC JIT.
Yeah.
Because of how the model works, it's based on the static compilation model and generating object file. People want to add the lazy JIT capability back, and that's one of the things before we can get rid of the old one.
Okay, the comment is that this is a side effect of the MC JIT, the new JIT engine that they're working on. And yeah, please at least leave this in there. Sorry, yeah.
The issue is more complicated than that.
Sure, we'll talk about, we'll take that offline because I'm nearly out of time anyway. Objective-C classes, I was going to have a moan about that. It'll compile them quite happily, but running them took me weeks. I had to go through my whole library and rewrite all of the Objective-C classes in there as nasty CPP Objective-C building wrapper workarounds. So that's a bit nasty. It's quite happy to call a method, but and it's quite happy to compile a class, but to actually get that class instantiated correctly in the static constructors for the module, forget it. Last slide, future possibilities. Like I said before, these editors could be anything. So I'll certainly be doing some audio editing tools that fit in there. But you know, the sky's the limit. There's any number of things you can do. Given here's a space, here's a database of all the code. Off you go. Put something in there. Also, another fun thing we could do is, because I've got an IDE that knows about the entire project structure and has LLVM in there, to run Clang-based refactoring, I could simply have a little text editor where you type in some C code that calls LLVM functions and runs that on the project itself. So, you know, I could add a whole library of custom refactoring functions and let you write them in the same way you might write a script for, or some of the Clang tools that are coming out now. I could just do that straight in there in the editor and so say, do it to my project. It'd be great to have a debugger in there. As far as I know, the LLVM stuff can't debug the JIT, or even get a stack trace from the JIT at the moment, but fingers crossed someone cleverer than me will figure that out. And recently I've also been thinking, I'd love to play with emscripting. I've already got a system that builds a project down into some LLVM bytecode. I could just pass that to emscripting. Sorry, what is emscripting? It's a compiler, it's a translator that takes LLVM bytecode and pumps out JavaScript. So you can compile C++ and run it in a browser. So I've already got almost all of that chain in place. And I've got a library that could easily be extended to run on JavaScript as well as my other platforms. So I'll be, as soon as I get a moment, I want to play around with that. And I think I'm out of time. And if we've got a minute left, questions?
If you go through the 5,000-foot view of exactly the mechanics of how this works, so you must have some executable that serves as a host for the target code that links in the LLVM library. And then what are you feeding it? C++ code or what?
Okay, the 5,000-foot, the question is, what is the 5,000-foot view of how this works? That's a really hard question. It's, there's one executable. I've linked directly into it the whole of the LLVM and Clang engine. That executable spawns a child instance of itself to actually do the JIT compile, to actually compile and run the JIT. The other half sits there as the IDE, and they talk.
So where does the code go? So you've got these source code files.
Mm-hmm.
How does that get married to the JIT? I mean, I'm passing text blocks over and telling the load file.
Okay, the question is, how do I get the source code to the JIT? The files are on disk. The project structure gets passed from the host application to the compile task. that's all. Basically, they both have a picture of the project which is kept in sync. When something changes in the editor, messages go out. It's all kept. The child process knows what all the files look like, and it triggers off a compilation, which it does locally. It caches byte code to disk.
So the host executable loads the source file, passes them off some function to LLVM, where it sets them up where it can get at some time compile them in memory. And then you can find the address of the function to invoke.
Yeah, the question is how do you invoke the thing when you've compiled it? Which is, what LLVM gives you is, once you've built your modules and passed them to the JIT engine, you can then ask for a function by name and call it. And even better, the running code can actually call any C function in your host app directly. It just calls it. And if the running code needs external libraries, you can just load the DLL into memory, and your JIT code can magically call all the functions in that DLL, which is really handy because it means you can basically run anything in a JIT. They can also pass pointers and whatever you want between them, so you can create a structure, pass it to the JIT, and pass it back, and pass function pointers back and forth. It works really well. Static libraries, you can. I haven't tried it, but I'm pretty sure the JIT you can give it a lib to load, and it will do it. It must do that. I've seen the function. I've never used it. Okay. Anyone else? I'm cutting into Louis' time, so.
Can you give me 30 seconds out in the hall?
Yeah. Anyone else?